Nice talk. Please, questions.
How can we use these defects in material?
How can you use these defects? Well, as I mentioned already, for example, if you create line defects in without moly disulfide or other dicalconjugate dyes which were originally insulating, you can create conducting channels. Basically, you can conduct electricity along these line defects. To this end, it's like engineering the electronic properties of the nanoscale. The impurities you can dope, like bulk systems. You can also dope 2D systems using impurities.
And this doping process can be completely controlled?
Oh, well, in principle, in theory, yes. Basically, when you dope your system at the growth stage, yes, depending on the concentration of basically what you put in during the growth, to some extent, yes. Still, like basically equilibrium. I mean, if you look at, if you want to know or have a very strict control, like how many atoms you have, let's say in 2 nanometer area, then maybe it's still not at that level. But in general, on the, let's say at least like tens of nanometer scale, it's fine. It works.
I'm just interested how is minimal scale of this process?
Я лучше по-русски скажу. Мне просто интересно. Не надо, мне так нормально. Мне просто интересно. Мне просто интересно, насколько маленьким управляемым можно сделать этот процесс. То есть, чтобы эти проводящие каналы, то есть, по сути, можно сделать печатную плату буквально с каналами в один атом. Это же возможно?
Yes, the question is how small the structures can be, and can we really use electron beam, if I understood correctly, to make that? Basically, the answer is yes. But still, this is like, for example, bonds in electron beam bond-induced rotations. It's still some sort of a, random process. But nevertheless, you can focus your electron beam now into the area about 1 angstrom. There is still some spread of the electron beam, but we're talking about, let's say, less than 1 nanometer.
А он, если мы его сфокусируем, соответственно, мощность у него увеличится. А он просто не выбьет атомы, там, например.
No, if your question is, if we focus the beam, will it knock out atoms? Basically, it depends on the voltage. If the voltage is low, below the threshold for knocking out atoms, you will knock out nothing. Still, some questions related to excitations and electron beam-induced etching remain, but in principle, it's doable what you are saying.
Please, question.
In any microscope, there are enough carbon atoms to make any chain. So the question about boron nitride chain, are there any evidences that it's really few boron nitride chain?
Yes, actually, we spent lots of time trying to understand if it's carbon or it's not. At least if you basically take a carbon chain, boron nitride chain, and what we really hoped for, pure boron chain, and then I calculated TM images and looked the experiment. Boron nitride chain was the best match.
Or how about BCM chain?
This we didn't look at. But boron chain would be like, it was the really driving force for this experiment, because in the boron chain, you should have very interesting Pyros transition, because it's not half filling up the band, it's a quarter filling up the band. And we should have not doubling of the unit cell size, but quadruple unit cell size.
My question is, if we use bilayer structures, for example, graphene and boron nitride. And we put perpendicular, maybe 3 layers. And we put electric field perpendicular these structures and put your electron beam. It's maybe change the defect formation.
Well, it can be minor effect, but not because of the field. What kind of field? The voltage difference you can put. Recall that I'm talking about 100 kilo-electron volt electrons.
Yeah.
And how much you can change, let's say, local potential on graphene. If you apply voltage, if I got your idea correctly. The question, the other question is that if you basically one shield, basically boron and screen graphene on the other way around.
Yeah.
It has been done already experimentally. Again, my coworkers did that. I wasn't involved in this project. They made graphene moly disulfide sandwich and put it into beam like this, then like that, and made like a triple sandwich.
Triple.
Yes. And the number of defects they got in each case was different. So it did matter, but it's like essentially, but it's not clear if it really, like, you know, more efficient damping electronic excitations, or it's simply, basically, you knock out atom if something is under, and it doesn't go to infinity in this case. But this has been done already. Actually, 2 papers published. One by Nanomaterial, by the way, from, well, anyway.
Okay. Что-то не работает-то. А может. О.
Насколько я понял, вы моделируете атомные и ядерные структуры. А почему нельзя моделировать электронно-ядерные структуры? Ведь даже в таблице Менделеева последние уровни, которые, в общем-то, участвуют в валентности, они, ну, вроде бы определены давно. Почему не моделируют электронно-ядерные структуры? Ну, ядерные, они видны всегда, это понятно. Но
Именно
ведь...
этим мы и занимаемся.
Нет, этим.
У нас есть ядра и есть электроны, которые
И-
большие Гольберга с некоторыми приближениями для всей системы.
То есть вы рассматриваете атомы как рогатые структуры?
Насчет рогатых я не уверен.
Нет, ну, то есть, ну, или микрокристаллические, что электроны расположены на некоторых фиксированных местах. И тогда можно моделировать.
Почему должен расположен в фиксированных местах?
Нет, но моделируется.
Ну, потому что электрон в материальном поле ядра, согласно элементарной механике, может зависать, потому что при ускоренном движении возникает сила сопротивления. И если учитывать не только силу кулоновского притяжения, но и отталкивание как материального потока, то тогда можно рассматривать именно как микрокристаллики. Спасибо.
Ну, в общем, спасибо за вопрос. Спасибо большое.
Perhaps it's the same. At the beginning, you have shown this that you simulated this knockout of atoms due to electrons, right?
Yes.
But
Knock-on damage, yes.
you don't actually simulate the electrons coming, right?
No.
You give kinetic energy to the atom, something like that, right?
Yes, because the transfer of energy to the nuclei occurs on the attosecond time scale, 10 to minus 24. It's instantaneous, basically, transfer of kinetic energy. And then the atom starts moving slowly. As I mentioned already, it's like a very speedy, energetic bullet hitting a big, heavy ball. And then the ball starts moving. It won't just go back. Basically, it's to transfer momentum, it should go like this. because it's positive basically, it was negative, but it cannot be absorbed by the system because the changes in the electron energy is very, very small. So essentially, you don't have to take into account the electron, it's gone. Long before the atom, long ago before atom starts moving.
So what you actually do, you give kinetic energy to
Yes,
one atom, right?
I assign initial kinetic energy to one of the atoms in my system and then do molecular dynamics with density functional theory forces.
Okay, thank you.
Yeah. Please.
I understand that in this type of talks it's very difficult and probably unnecessary to go into technical details. But
That's a slide for you.
Still, I guess you used different level of approximations, or all calculations were done at the same level. So I guess sometimes you use GJ, sometimes...
Depends again. There are so many papers here.
Yeah, exactly. So the question is, in using a lot of different approximations to this type of problem, can you give an advice or a kind of summary? When the simplest approximation, such as GJ, is sufficient, when you really need to go to van der Waals, when you need to go beyond GJ plus van der Waals, go to GW or probably hybrids. So some kind of summary and experience.
The question is what you are aiming at, what you would like to calculate. If you want to calculate knock-on damage,
yes,
DFT with GGA should be and the MD should be perfectly fine.
Are you sure? Because we are dealing with defects. Defects create levels in a gap, and if a gap is wrong, then the entire defect creation process may be completely wrong.
Well, I would say with highly conducting, at least in graphene, the agreement between experiment and theory is pretty good.
Yes.
Of course, you can get about 10% difference depending on the simulation setup and again, functional using LDA or GGA, but more or less the same. In semiconductors and insulators, then it's much more tricky. Because the electronic structure may not be in the ground state.
Yes.
Even though if
exactly
you look at the current,
yes.
basically like a standard current, the electron goes through like 1 square nanometer every like millisecond. So it's not very frequent electrons go through. Even like orders of magnitude higher. But still, in principle, there is a recipe, time-dependent density functional theory, and we did some calculations already, but it's bloody expensive, as you may know. Approximately 10,000 times more expensive than standard DFT.
One still should be a little bit careful with.
Question, please. Can you take into account the influence effect for molecular interaction between different kind of layers?
You are talking about like van der Waals.
Van der Waals, yeah.
Yes, well, I had several slides. Basically, we tried several approaches at different levels. Well, you do it on top DFT calculations anyway. You first do standard DFT calculations, and then, like, you calculate van der Waals interaction. Either empirical way, the simple Green corrections, which doesn't work very well. But then you can use specially designed exchange correlation function, which take into account van der Waals interaction. Physically, it's there, and from density here, from density there, and some sort of basically operator, which takes into account the interaction. Or do the most accurate calculations at the random phase approximation level. Essentially, some sort of perturbation theory on top of standard DFT calculations. So, yes, you can, but again, as usual, the more accurate calculations get, the more expensive they are.
Yeah. But have some experiments with this for estimate this influence
For experiments, we can get the biggest of van der Waals interaction. But not for many, it's quite tricky by itself.
Yeah.
For graphite, it's more or less known, Dmitry, by the way, got value of the same order of magnitude as for molten disulfide as we did. Then there is a big group of experiments called liquid exfoliation, which actually, and they consistently get values smaller by a factor of 2. And the origin of this is not known, because let's say computationally, other groups got exactly the same what we did. But since pattern values are smaller, but again, I will not bet my life that the experiment is correct. It's quite tricky way how they extrapolate the random Poisson interaction between like basically layered molecules and the substrate.
Thanks. Please, question.
Is it possible to reproduce the periodic structures of defects by electron beam?
In principle, yes.
By that?
Well, if you essentially can, well, the simplest case, because you can focus the beam in predetermined areas, you basically knock atoms here, knock out atoms there, and in principle this has been done. You still have a statistical process. There is some, I would say, the question is, what kind of spatial accuracy you want to have. If you are happy with 1 nanometer, then the answer is definitely yes.
Maybe is it possible to use diffraction pattern to do that or not?
Well, from diffraction pattern you can get the idea about orientation of your, let's say, microcrystallites, for example.
No, I mean the diffraction pattern of electrons.
I mean, proton as well, but in principle, you mean that when you have like get amorphous structure, then I don't have it actually here, for example. Well, basically, just a second. Maybe it's not a very good example, and it's very dark. You can't see it here, diffraction pattern. Essentially, yes, when you get amorphous system, or it's still crystalline, you can get an idea about how many defects and how amorphous the structure is, probably from diffraction pattern.
No. I mean, you can produce diffraction pattern of electrons, and then you put such a beam to the surface. So you have at this position the maximum, at this position minimum for electron beam, and you can produce different intensities.
No, that's not.
You just get mask.
I'm sorry. Such structures are used for self-organized monolayers are used for patterning of different structures on the different surfaces.
But at least not in the microscope. Dmitry may comment on that, but I doubt that in microscope you can do it. Because you're talking about the real space first of all, not about reciprocal space.
Diffraction pattern, I don't understand which one is diffraction pattern.
Well, I understood.
So which you get in TM?
Yeah.
Diffraction pattern, it's only to understand what you get.
Basically, yes.
You cannot use it for creation of anything.
So my answer is no.
You see what you have, but you cannot use diffraction pattern as a tool to make difference.
Yes.
You can analyze only the
I suppose maybe we finish and continue on our table, another table. Yeah, thank you for